In this lecture we will talk about number systems. In many cases you're probably only used to one number system, so you've been operating in the decimal number system most of your life, and now we're going to talk about a little bit different way to represent numbers, specifically focusing on how computers represent numbers. So to get started, let's talk about the decimal number system that all of you are familiar with. This is the number system you've been operating in your entire life up to this point. So you think about how we do arithmetic or how people count. You just go 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Then you add an extra digit, you get to 10. You can count from there 10 up to 99 using just 2 digits. Then you have to add a third digit to get to 100, etc. And so this is considered base 10. So every place in the decimal number system has a certain value, and they are progressive powers of tens. So you have your ones place, your tens place, your hundreds place, thousands, etc. And those are representative of different powers of 10. So 1 is 10 to the 0, 10 is 10 to the 1, 100 is 10 squared, 1000 is 10 to the third, etc. And then if you go to the right of the decimal place, you also have negative powers of 10. So you've got your tenths place, which is 10 to the negative 1. You've got your hundredths place, 10 to the negative 2. And it can keep on going down to smaller and smaller values the further you go to the right. And what digits do you have available? So in each place, you can have a value 0 through 9 inclusive. So we can generalize that and showcase that a variety of numbers can be used as a base, not simply just 10. So in general, any integer 2 or greater can serve as the base of a number system. You may also see this termed as the radix of a number system. So base or radix are used interchangeably. The digits available in any given base are 0 through n minus 1 inclusive. So for base 10, that was 0 through 9. We're also going to focus in this class on binary, which is base 2, and in that case the digits available will be 0 and 1. We'll also talk about base 16, or hexadecimal, and in that case you'll have digits to represent 0 through 15. We can talk about a variety of other bases. So for example, base 6, which is not really used for much other than mathematical examples, but if you were to use base 6, every place would be a progressive power of 6. So as you move further to the left, you would have your ones place, your six place, your 36, which represents 6 to the 0, 6 to the 1, 6 to the 2, etc. One of the things that you'll notice is no matter what base you're using, there's always a ones place. So that is because anything to the 0 power happens to equal 1. And in the case of base 6, you'll have digits 0 through 5 available. So how are we going to notate bases? Because we're going to use a variety of bases in this class, and it may not be entirely clear as to which base we're talking about, we're going to be using a subscript so that you know that we're talking about a specific base. So for example, if we had 15 with this little subscript 3, that would indicate that 15 were in base 3. Now, what would that be worth in decimal? That's right. So the 1 would be worth a 3 to the 1, or 3, and then that 5 would be in your 3 to the 0 place. So you would have 3 plus 5, that would be worth 8 in base 10. If we go back to decimal, how are we going to notate that? So the 25 that you've been used to your entire life, to make sure we know that that is in decimal, we're just going to put a little subscript 10 out there to showcase that it's in base 10. So let's talk a little bit about the binary number system. This is how computers represent and store information. They use binary to encapsulate a lot of different data. So why do computers like to use binary? Well, it's base 2, and so every digit in there is either a 0 or a 1. And as we talked about before, digital systems like to represent things as either a logic 0 or a logic 1, which represents either an on or an off, or represents a true or a false. It's one or the other. So computers are very good at switching between one level and another. They're not as good at figuring out gradations in terms of where we are in between two large values. They generally just like to make an arbitration in terms of deciding this is logic level high, this is logic level low. So what will happen is computers will establish a voltage to represent a logic 1 or a true statement, and they will establish a voltage to represent a logic low or a false statement. You can correlate that to ons or offs. And if that voltage level happens to be higher than whatever the threshold is for a logic high, then it will be processed as a logic high. If it happens to be lower, it'll be processed as a logic low. In some cases, there's some voltage ranges in the middle. So you might have, let's say, 0 through 2 volts is processed as a logic low, and then 3.5 through 5 volts is processed as a logic high, and anything that happens to be in the middle there is sort of considered a no man's land, where you really just don't know whether the computer is going to process it as a 0 or a 1. So it's very important in digital circuits to make sure that your voltage levels are clearly within the ranges that are defined as logic 1 or logic 0. But in any case, that's chasing a little bit of a tangent. We just want to make sure we understand that computers operate in base 2. So they make decisions based upon everything either being a 1 or a 0. And so in that case, you only have 0 or 1, which, as we mentioned, is very easy to represent electronically. So let's look at how we can count in these different number systems. So going back to counting in decimal, which you've been doing most of your life since you were children and first learned to count, in decimal we simply just keep adding 1. So we start out at 0 and go 1, 2, 3, on up through 9. Once we reach 9, we run out of what we can represent with a single digit. So we've got to perform a carry, which, as you saw in the abacus video, just means that you zero out that particular place, and then you increment the next place to the left. So the same thing will happen in all of the bases that we will talk about. So in decimal, that happens when you reach 9. And in other bases, that happens when you reach any value beyond n minus 1. So 9 we can represent with a single digit. If we needed to represent 10, we would have to zero out that 9 and carry on over to put 1 into the next place. So if we look at binary, let's think about how we would go about counting. So 0 can be represented here as 0, 0, 0, 0. 1 represented as 0, 0, 0, 1. And the question is, what comes next in that sequence? Well, if you simply add 1 to that rightmost digit, you're going to get 2. And we cannot hold 2 in a binary bit there. And so what we're going to have to do is actually clear out that rightmost place and increment the 1 space to the left. So the next value would be 0, 0, 1, 0. Okay, what do you suppose is going to come next? That's right, it's going to be 0, 0, 1, 1, and then the next value after that? Well, the next value after that is going to result in 2 carries. So you'll try to add a 1 to that rightmost one, and then it won't have space to hold that, so you have to carry out. Now you have another 1 being added together, you have to do a carry out, and you'll end up with 0, 1, 0, 0. So it's very similar to what you saw in the abacus video. So let's talk a little bit about some of the terminology that's used when dealing with binary. So a lot of this is in terms of how we talk about individual components of a binary value or a binary number and how binary digits are arranged. So in this case, each binary digit is referred to as a bit. So if we're talking about a single 1 or a single 0 in a sequence, those individual 1s or 0s can be referred to as a bit. Generally, we cluster these bits together. So digital systems are usually based upon registers. Registers put together several bits. We'll talk about registers later on in the course. But if you have a group of 8 bits together, that is referred to as a byte. And you're probably very familiar with the term bytes, or more typically megabytes or gigabytes in terms of file sizes or in terms of hard drive size, those types of things. A group of 4 bits is called a nibble. So sometimes you'll see a high nibble and a low nibble as part of a byte. Apparently whoever came up with this terminology must have been rather hungry at the time. So you have a bit, then you have a nibble, then you have a byte. Another term that's often used is the least significant bit, and that is the rightmost bit in a binary number. So if you think about that, think about how we represent currency in this country. So generally, we take currency out to 2 decimal places to represent the number of cents, and then to the left of the decimal, we have the number of dollars. So the rightmost bit there, or the rightmost digit that we have when we're talking in our decimal number system in terms of currency, is only worth a penny. And then if you go just the one place immediately to the right of the decimal, that's worth 10 cents or a dime. Then to the left of the decimal, you've got your dollars place, then your $10 place, your $100 place. And so the further you go to the left, the more valuable that position is, and the further you go to the right, the less valuable that position is. So the rightmost is considered the least significant bit, because when you have a 1 there in binary, that adds the least value to your quantity. Likewise, the leftmost bit is going to be called the most significant bit, or MSB. And generally, systems are quite restricted in terms of how many bits they have available. So systems are designed to hold specific values. Oftentimes they're designed for the largest possible value they think will need to be represented, and anything beyond that will not be able to be stored. So you may have seen that in terms of some gauges, where gauges can only go up to certain values. You can think about that just like a tank of water. If a tank of water is designed to hold a specific number of gallons, and you add 1 more gallon beyond that, it simply cannot hold anymore, and so you might have a problem. And so an example is that modern operating systems are typically 64 bits. And when you talk about the number of bits that you have available, you can use that to represent 2 to the power of that many bits. So for example, with a 64-bit operating system, you can represent values between 0 and 2 to the 64, which is a very large number. Early microprocessors only operated with a 4-bit architecture. So in that case, you could only represent values between 0 and 15. And if you needed anything larger than that, you would have to group a couple registers together. And one side note on that, the reason that we shifted over to a 64-bit operating system as the standard is that when we were operating on 32-bit operating systems, which really was the standard until just a few years ago, you could only address 2 to the 32 registers. Now if you do the math on that, that works out to be about 4 billion, which seems like quite a large value, but really that's only 4 gigabytes. So if you needed to interface with more than 4 gigabytes of RAM or a 4 gigabyte memory card or things like that, you could not do that with a 32-bit operating system. So that's why modern operating systems work with 64 bits. That gives you many more addresses to work with, so you can represent things that are quite large. And I imagine at some point in your lifetime that will be too small, and we're going to end up with 128-bit or 256-bit operating systems, or maybe we'll just have completely different digital systems altogether. But that number will only get larger as technology emerges and improves. So some other terminology to look at: when you have a value that's larger than anything you can represent, that's called an overflow. So if you go back to that example of water in a tank, if you have a tank designed to hold 500 gallons and you put 501 gallons in it, that tank will overflow. And so you're going to have some way for that to be represented, or just to indicate that you cannot hold the value that you're trying to put in there. Carrying and borrowing in arithmetic operates very similarly to what you've been used to all along in the arithmetic that you've done. So in elementary school, somewhere you learn to add values together, you learn to subtract values, and along with that, you realized if you had a value larger than 10, that involved a carry out to the next digit. And if you had a value such that you could not subtract something from another value, you needed to borrow from the left. And we saw some of that happen in that abacus video. This will operate very similarly in binary, but in this case, the carries and the borrows will happen with 2s rather than with 10s, as you have seen in decimal. Let's talk a little bit about how to convert from one base to another. And first, let's start with, how do you convert from binary back to decimal? So if you happen to see a binary value, oftentimes most people don't think about binary values natively in binary. We like to think, well, how much is that worth in the decimal number system that we're used to? So one of the things we need to do is figure out how to convert from binary back to decimal. So here's an example. If you have 1010 down here, remember that each of these places is worth a power of 2. So for 4 binary bits, this leftmost is worth 2 to the 3, this is worth 2 to the 2, 2 to the 1, 2 to the 0. And so what we can simply do is take the value that's here, multiply that by the power of 2 that it represents, and add them all together. So 1010 would represent 1 times 2 to the third plus 0 times 2 squared, and you can see the rest there. Once you add that all up, that works out to be simply 10. So 1010 in binary represents 10 in the decimal number system. This would be a good time for you to pause the video so you can work through the examples that are on the screen. Okay, and we're back. So hopefully if you worked out this math, you saw that the first example turns out to be 1100 equals, that's right, 12. And the next value there, 0110, what did you get? Hopefully 6, that's right, 6 is the correct value there. And then 1111, what did you get there? That should be 15, correct. So hopefully you got those values. If you didn't figure out those values, you might want to go back and look at the example on the previous slide, see if you can figure out where you went wrong. The next thing we want to do is reverse that process. So if we have a decimal value, we want to figure out how to represent that in binary. And there's actually a couple different ways to do that. And so the way that's in your book is a little bit different than the way that I learned it. I'm going to showcase both ways to you. I don't really care which way you use, so long as you figure out one way to convert from decimal to binary. So the first way is to actually compare the value that you're trying to represent to the progressive powers of 2. And what you want to search for at first is the largest power of 2 less than or equal to the decimal value you're trying to represent. And so that's going to be the first place you're going to have to deal with. You know, anything larger than that, you're not going to have any of those values. You're going to have zeros there. So the first place you're going to have a 1 is going to be in the largest power of 2. So let's take a look at an example of that. Once we get that, then we're going to keep going on to smaller and smaller powers of 2 until we can represent the full number. So if we do use this method, let's start out with 136 in decimal and see if we can convert it to binary. So the first thing we want to do is look at our powers of 2. And so I've listed out several different powers of 2. This list could go on and on forever. But these are the relevant values we need to take a look at. So we know that 136 is greater than 1, greater than 2. We keep going. It's greater than 128. It is not greater than 256. So we know that in the 256 place, on out, all of those digits are going to be zeros. And we need to hone in on 128 and smaller. So we know we're going to have a 1 in that 128 spot. So let's start out and say, okay, we know 128 is the largest power of 2 less than or equal to 136. And that tells us we're going to need 8 binary digits. How do we know that? Well, we know we're going to have a binary digit to represent 128. And as a result, we're going to have a binary place for all of these values that are smaller than that. So that's going to end up with 8 total binary digits to represent this value. So let's go ahead and subtract our 128 from our original value of 136. So that's going to represent that first 1. And so our current binary value is going to be 1, and then we know there's 7 other values that we're going to have to fill in. And so we're going to make this sort of like a game of hangman, if you remember playing that game when you were a child, where you had to fill in a puzzle with specific letters. In this case, we're going to be filling in this puzzle with zeros and ones as appropriate. So for right now, that leading 1, not knowing anything about what the next digits are going to be, that leading 1 represents 128 of the total 136 that we need to represent. So now we know with the remaining spaces, we need to represent a value of 8. So we're going to take that 8 and compare that to the next powers of 2 on down the line. So we've already dealt with our 128. Our next power of 2 is 64. And so we know 8 is less than 64, so we're not going to have a 1 there. That's going to be a 0. So we can go ahead and put a 0 in the 64's place. As we keep on going, we know that 8 is not greater than or equal to 32 or 16 as well. So we can fill in 2 more zeros on our chart. So now we've got 1, 0, 0, 0, and we still have 8 to represent, and we've got 4 more places to fill on in. Now our next place is worth 8, so we have a remaining value of 8. The next power of 8, our next power of 2 happens to be 8. So when we do that comparison, we realize, hey, that works out. So we're going to put in a 1 in our 8's place. Once we subtract the 8 from the 8, we realize we've represented the entire value. We have 0 left to represent. Now we can't simply stop there and say the binary value is 1, 0, 0, 0, 1. We have to recognize that there's 3 more places that need to be filled in. But because we have no more value to add in those 3 more places, we can simply fill those remaining 3 slots with zeros. So our final answer is going to be 136 in decimal happens to equal 1, 0, 0, 0, 1, 0, 0, 0 in binary. So that's one method to solve from decimal to binary. The other method that happens to be in your textbook, and you can read about this in more detail starting on page 9 in your textbook, is using what's called successive division by the radix. So in this case, the radix happens to be 2. We're operating in binary or base 2. So what we're going to do is continue to divide by 2 every time. So we're going to start out with our 136 again and see if we can get the same result using this method. So if we take 136, divide it by 2, what we'll end up with is 68 with a remainder of 0. So we're using this long division technique that you probably learned somewhere back around, I don't know, 4th or 5th grade, whenever you cover long division. So we're not converting this all the way out to a decimal representation with fractional values. We're looking at integer remainders and integer quotients. So we've got 68 remainder 0. Now we're going to take that 68, divide that by 2, and see what the remainder is in the quotient. So that gives us 34 with a remainder of 0. Then we're going to keep going. So 34 divided by 2 gives us 17, remainder 0. 17 divided by 2 gives us 8, remainder 1. And we can keep on going through this process, taking that quotient and then continuing to divide that by the radix. We're going to keep going until the quotient works out to be 0. So right now we have 1 with a remainder of 0. We've got to take that 1, divide by 2. That gives us a quotient of 0 with a remainder of 1. Now you may be thinking, what the heck am I doing with all this? When am I going to figure out a binary value? Well, if you look at the remainders and you assemble them from bottom to top, stringing them together, each of those remainders is the final value in your binary representation. So if you start down here at the bottom, this is your most significant bit, all the way up through your least significant bit up here at the top. So we end up with the same final answer, 1, 0, 0, 0, 1, 0, 0, base 2, or binary, happens to equal our original 136. So you can use this method. This is also nice. You can use this same method for converting to other bases, but instead of using 2, you would use whatever base it is that you're interested in at the time. So this would be another place for you to check your understanding. Go ahead and pause the video, see if you can work out these two problems. Okay, and we're back. So hopefully what you figured out was 25 decimal works out to be 11001. And hopefully you found out that 100 decimal works out to be 11001000. If you didn't get those values, you might want to review the previous slides and see if you can figure out where you went wrong. So a few notes on the use of binary. Generally in digital systems, the number of bits is a multiple of 4. So you might have a 4-bit system, 8-bit system, 16-bit system, and so generally your binary values are going to be clustered into groups of 4. Now you may not need an entire group of 4 to represent a value, or you may have kind of one straggling bit. So in this example, if you converted 17 to binary, you would need 5 binary digits to represent that. But if you had to represent that in a real system, generally you'd need at least 8 bits, and so you would just simply pad the leading values with zeros. Another base that's very commonly used by computer scientists and engineers is hexadecimal. So this allows us basically to use a shortcut to represent binary values. Hexadecimal is base 16, so hex is 6, decimal is 10. You add those together, base 16. And this is used quite a bit, but there is one issue with this particular base. So in this case, just as we remember with the other bases, we can represent values using digits 0 through n minus 1. Well, there's a problem in that n happens to be 16, so we need a single digit that's going to represent 10, 11, 12, 13, 14, and 15. If we were to simply plug in 10 or plug in 11 whenever we needed it, it would be confusing to the person reading the number. They wouldn't know if that meant 10 in that current place, or if you meant for that 1 to actually go one place to the left. So what we can actually do is represent 0 through 9 exactly the same as we've done in the decimal number system, but we're going to use letters to represent larger values. So A is going to be used to represent 10, B for 11, on up through F for 15. So 0 through 9, and then A, B, C, D, E, F, for the values 0 through 15. So the conversion follows a very similar process. So you can go through either of the methods that we talked about. You can look at which power of 16 happens to be less than or equal to the value you have left to represent, and keep on representing different powers of 16 as we go. Or you can do the successive division representation as you've seen there. So let's first look at a decimal to hexadecimal conversion. So let's look in this example at trying to convert 2003 base 10 or decimal over to hexadecimal. You may also see hex used as a shorthand for hexadecimal. So oftentimes computer scientists, computer engineers will refer to hex instead of the full hexadecimal. So if we look at the powers of 16, we've got our 16 to the 0. Again, we always have a ones place. Then we got 16 to the 1 or 16, 16 squared or 256, 16 to the 3, 40, 96. So if you look at those powers of 16, that ought to tell you how many hexadecimal or hex digits you're going to need. So you know you're not going to need this 4096 place because that's bigger than the value you have to represent, but you are going to need a 256 place, you are going to need a 16s place, and you are going to need a 1s place. So if we start with our 256s, the other question that we need to ask now, since we're not simply in binary where we choose whether or not we're going to take 256 out, we have to figure out how many 256s we can take out of 2003. So how do we figure that out? Well, we need to do a little bit of arithmetic. So if we look, we can determine that 7 times 256 is 1792. 8 times 256 is 2048. 2048 is bigger than what we're representing, so we're not going to get all the way to 8. But 7 times 256 is smaller. So our first digit, our first hexadecimal value, is going to be 7. And that represents 7 256s that we're going to take out of 2003. So we'll put that down as our first digit, and we're going to go ahead and subtract 7 times 256 from that 2003, and that gives us a remainder of 211 that needs to be represented in the next two places. So now we need to look at 211, compare that to 16. We know that 16 is in fact less than or equal to 211, and now the question is how many 16s can we take out of 211? So if we go ahead and do similar mathematics there, we realize that 13 times 16 is 208, 14 times 16 is 224, so 208 is less than 211, 224 is too big, so we're going to take 13 of them away. So we have to represent 13, and if you remember, we can't just plunk down 13 as our next value. We have to convert that over to the character that represents 13. And which character was that in hexadecimal? Well, A is 10, B is 11, C is 12, so we're going to have to put down D. So the correct answer is D. So our next value is going to be D. At this point, we've got 7, and we've got D, and that's represented quite a bit of our value thus far. How much? Well, we'll take away our 208, which is what the D is accounting for, from the 211 that we had left to represent. And so that tells us we have 3 left to represent in that last value. So out of our original 2003, we've represented 2000 with the 7D and some value thereafter, and we have to figure out what that last value is to represent the remaining 3. Well, the last digit's really quite easy. So from this point, that's our ones place. And the question is, how many 1s does it take to make a 3? And obviously the answer there is 3, so our last digit has to be 3. The final answer when we convert 2003 decimal into hexadecimal is 7D3 base 16, or hexadecimal. So let's give you a moment to practice here. So for this problem, what I want you to do is try to convert 234 decimal or base 10 over to hex. So you can use the method we just talked about, or you can use successive division. But remember, if you use successive division, that you're going to have to do division by the number 16, which is your base here, rather than using base 2, which you used before. So I'll give you a moment to pause the video and see if you get the correct answer. Okay, and we're back. So hopefully what you figured out is the answer is EA. Okay, that is EA. If you did not get EA as your answer, you may want to review the previous example and see if you figure out where you went wrong. So this is where the class stopped, and we will pick up right here on Friday in the lecture.